Good day, this is Shinamiya Pagaduan from BSED Math 2A, and for today's video, I will discuss Chapter 4.1 Vector Spaces. In this lesson, we will talk the vectors and some general definition of a vector. To start, let us define first what is vector. Vector is derived from the Latin word vectus, which means to carry. The idea is that if you were to carry something from the origin to the point x1 and x2, the trip could be represented by directed line segment from point 0, 0 or the origin to x1 and x2. Vectors are represented by lowercase letter set in boldface type, such as u, v, w, and x. Vectors in the plane. A vector in the plane is represented geometrically by a directed line segment whose initial point is the origin and whose terminal point is the point x1 and x2 shown in the figure. A vector is represented by the same ordered pair used to represent its terminal points. X is equal to x1 and x2. x1 and x2 are the component of vector x. There are two vectors in the plane. U is equal to u1 and u2, and v is equal to v1 and v2. The two vectors are equal if and only if u1 is equal to v1 and u2 is equal to v2. Let's try an example. Use a directed line segment to represent each vector in the plane. Letter A, u is equal to 1 and 4. In letter B, v is equal to 2 and negative 2. Solution. To represent each vector, draw a directed line segment from the origin to the indicate terminal point. Like in letter A, I draw a directed line segment from the origin indicated to the terminal point, which is 1 and 4. And in letter B, I draw a directed line segment from point 0, 0 to point 2 and negative 2. Before we proceed in the operation with the vectors in the plane, let's first discuss the Theorem 4.1, which has 10 properties and play a fundamental role in linear algebra. In fact, in the next section, you will see that it is precisely these 10 properties that have been abstracted from vectors in the plane to help define the general notation of a vector space. Theorem 4.1, Properties of vector addition and scalar multiplication in the plane. Let u, v, and w be vectors in the plane, and let c and d be scalars. Number 1. U plus v is a vector in the plane, closure under addition. 2. U plus v is equal to v plus u under commutative property of addition. 3. U plus v plus w is equal to u plus v plus w. This is associative property of addition. 4. U plus 0 is equal to u, additive identity property. 5. U plus negative u is equal to 0, additive inverse property. The next 5 properties are under scalar multiplication in the plane. 6. Cu is a vector in the plane, closure under scalar multiplication. 7. C multiplied by u plus v is equal to cu plus cv under distributive property. And number 8, c plus d multiplied by u is equal to cu plus du, distributive property. 9. C multiplied by DU is equal to CD multiplied by U, associative property of multiplication. And 10, 1 multiplied by U is equal to U, multiplicative identity property. Let's prove some properties. The proof of each property is a straightforward application of the definition of vector addition and scalar multiplication combined with the corresponding properties of addition and multiplication of real numbers. For instance, to prove the associative property of vectors addition, you can write U plus V plus W is equal to U1 and U2 plus V1 and V2 plus W1 and W2. Take note that when we add a vectors in the plane, we need to add their corresponding components. Then it became U1 plus V1 plus W1 and U2 plus V2 plus W2. Using associative property, U1 plus V1 plus W1 and U2 plus V2 plus W2 is equal to U1 and U2 plus V1 plus W1 and V2 plus W2 is equal to U1, U2 plus V1, V2 plus W1, W2 is equal to U plus V plus W. Let us also prove the distributive property of scalar multiplication over addition. C plus D multiplied by U is equal to C plus D multiplied by U1 and U2 is equal to C plus D multiplied by U1 and C plus D multiplied by U2 is equal to C U1 plus D U1 C U2 plus D U2 is equal to C U1 and C U2 plus D U1 and D U2 is equal to C times U1 U2 plus D times U1 and U2 is equal to CU plus DU. Now that we already know the 10 properties of vector addition and scalar multiplication in the plane, we proceed in adding two vectors in the plane. Vector addition is the first basic vector operation. This is used to add two vectors in the plane. Remember that when we add two vectors, we add their corresponding components. That is, U plus B is equal to U1, U2 plus V1, V2 is equal to U1 plus V1, and U2 plus V2. Also, the sum of two vectors in the plane can represent us geometrically. Let's have an example where U is equal to 1, 4, and V is equal to 2 and negative 2. To add the two vectors, we have U plus V is equal to 1, 4 plus 2 and negative 2. By adding the corresponding component of U and V, we get 1 plus 2 and 4 plus negative 2 is equal to 3, 2. Geometrically, the sum of two vectors in the plane is represented as the diagonal of a parallelogram having U and V as its adjacent sides, as shown in the figure. Let's have another example. In this example, we will solve the vector 0, 0, called the zero vector, denoted by 0. Find the sum of the vectors. U is equal to 3 and negative 2. V is equal to negative 3 and 2. Solution. U plus V is equal to 3 and negative 2 plus negative 3 and 2. is equal to 3 plus negative 3, and negative 2 plus 2 is equal to 0, 0. Let's check the graphical represented of zero vectors. As you can see in the figure, we can see that the zero vector is not pointing in any particular direction, so it has an undefined direction and with no length. Another basic vector operation is the scalar multiplication. To multiply vector v by scalar c, we multiply each component of vector v by scalar c. It becomes Cv is equal to C times V1, V2 is equal to CV1 times CV2. Recall from chapter 2, scalar is used to mean a real number. This usage arose from the fact that multiplying a vector by a real number changes the scale of the vector. For instance, if a vector v is multiplied by 2, its resulting vector 2v is a vector having the same direction as v and twice the length. In general, for a scalar c, the vector cv will be c times as long as v. If c is positive, then cv and v have the same direction. And if c is negative, then cv and v have opposite direction. As shown in the figure, the product of a vector v and a scalar negative 1 is denoted by negative v is equal to negative 1 times v. The vector negative v is called the negative of v. The difference of u and v is defined as u minus v is equal to u plus negative v. And you can say v is subtracted from u. Let's have an example in scalar multiplication. Provided with v is equal to negative 2 and 5 and u is equal to 3 and 4, find each vector. In letter A, 1/2 v, B, u minus v, and in C, 1/2 v plus u. Let's solve letter A first. In letter A, we have 1/2 v. Since the value of v is equal to negative 2 and negative 5, we need to substitute v. Then it became 1/2 multiplied by negative 2 and 5. Remember, when multiplying a vector by scalar, we need to multiply each of the component of vector by the scalar. So, 1/2 v is equal to 1/2 times negative 2 and 1/2 times 5 is equal to negative 1 and 5/2. Let's proceed in letter B. U minus v. By substitute the value of u and b, we get 3 and 4 minus negative 2 and 5 is equal to 3 minus negative 2 and 4 minus 5 is equal to 5 negative 1. Next is C, 1/2 v plus u. Using the result in part A, where 1/2 v is equal to negative 1 and 5/2, we get negative 1 and 5/2 plus u. By substitute the value of u, we get negative 1 and 5/2 plus 3 and 4. By adding the corresponding component, we get negative 1 plus 3 and 5/2 plus 4 is equal to 2 and 13 over 2. Our next topic is vector in n-space. The discussion of vectors in the plane can now be extended to a discussion of vectors in n-space. A vector in n-space is represented by an ordered n-tuple. For instance, an ordered triple has a form of x sub 1, x sub 2, x sub 3. An ordered quadruple has the form x sub 1, x sub 2, x sub 3, and x sub 4. And the general ordered n-tuple has the form x sub 1, x sub 2, x sub 3, up to x sub n. The set of all n-tuples is called n-space, and it's denoted by r raised to n. R raised to 1 is equal to 1 space is equal to set of all real numbers. R raised to 2 is equal to 2 space is equal to set of all ordered pairs of real numbers. R raised to 3 is equal to 3 space is equal to set of all ordered triples of real numbers. Up to r raised to n is equal to n space is equal to set of all ordered n-tuples of real numbers. The practice of using an ordered pair to represent either a point or a vector in 2 space continues in n space. That is, an n-tuples x sub 1, x sub 2, x sub 3 to x sub n can be viewed as a point in n space with the xi as its coordinate or a vector. X is equal to x sub 1, x sub 2, x sub 3 to x sub n with the x as its component. As with vector in the plane, two vector in n space are equal if and only if the corresponding component are equal. The sum of two vector in n space and the scalar multiple of a vector in n space are called the standard operation in n space. So let u is equal to u1, u2, u3 up to un, and v is equal to v1, v2, v3 up to vn, be a vector in n space. And let c be a real number, then the sum of u and v is defined as vector. U plus v is equal to u sub 1 plus v sub 1, then u sub 2 plus v sub 2, u sub 3 plus v sub 3, up to u sub n plus v sub n. And the scalar multiple of u by c is defined as the vector cu is equal to cu sub 1, cu sub 2, cu sub 3 up to cu sub n. As with 2 space, the negative of a vector in n space is defined as negative u is equal to negative u sub 1, negative u sub 2, negative u sub 3 up to negative u sub n. And the difference of two vector in n space is defined as u minus v is equal to u sub 1 minus v sub 1, u sub 2 minus v sub 2, u sub 3 minus v sub 3 up to u sub n minus v sub n. The zero vector in n space is denoted by 0 is equal to 0, 0 up to 0. Let's have an example in standard operation of n space. Provided that u is equal to negative 1, 0, and 1, and v is equal to 2, negative 1, and 5 in 3 space, find each vector a, u plus v, b, 2u, and c, v minus 2u. Let's solve first the letter a, u plus v. Substitute the value of u and v, then u plus v is equal to negative 1, 0, and 1 plus 2, negative 1, and 5. Remember, when we add two vector, we add the corresponding component, where u plus v is equal to negative 1 plus 2, 0 plus negative 1, and 1 plus 5 is equal to 1, negative 1, and 6. Letter B, 2u is equal to 2 multiplied by negative 1, 0, and 1. By multiplying a vector by a scalar, we multiply each component by the scalar. Then 2u is equal to 2 multiplied by negative 1, 2 multiplied by 0, and 2 multiplied by 1 is equal to negative 2, 0, and 2. Next is letter C. v minus 2u. Using the answer in letter B, we can substitute 2u is equal to negative 2, 0, and 2. Then v minus 2u is equal to 2, negative 1, 5, minus negative 2, 0, and 2. Subtract the corresponding component, it became 2 minus negative 2, and negative 1 minus 0, and 5 minus 2 is equal to 4, negative 1, and 3. Also, the vector addition and scalar multiplication for vector in n space has 10 properties. The following properties are the same as those listed in Theorem 4.1 for vector in the plane. Using these 10 properties from Theorem 4.2, properties of vector addition in scalar multiplication in n space, we can perform algebraic manipulation with vectors in n space in much the same way as you do with real numbers, as demonstrated in the next example. So let u is equal to 2, negative 1, 5, 0, v is equal to 4, 3, 1, and negative 1, and w is equal to negative 6, 2, 0, and 3. Be vector in 4 space. Solve for x. Letter A, x is equal to 2u minus v plus 3w. To solve in letter A, x is equal to 2u minus v plus 3w is equal to 2u minus v minus 3w using the distributive property. Substitute the value of u, v, and w, then it became 2 multiplied by 2, negative 1, 5, 0, minus 4, 3, 1, and negative 1, minus 3 times negative 6, 2, 0, and 3 is equal to 4, negative 2, 10, 0, minus 4, 3, 1, negative 1, minus negative 18, 6, 0, and 9. The next step is subtract the corresponding component. Then 4 minus 4 minus negative 18, negative 2 minus 3 minus 6, 10 minus 1 minus 0, and 0 minus negative 1 and negative 1 is equal to 18, negative 11, 9, and negative 8. Therefore, the value of x is equal to 18, negative 11, 9, and negative 8. Let's now proceed to the zero vector in n space, or called the additive identity in n space. Similarly, the vector negative v is called the additive inverse of v. The Theorem 4.3 summarizes several important properties of the additive identity and additive inverse in n space. Theorem 4.3 Properties of additive identity in and additive inverse. So let v be a vector in n space and let c be a scalar. Then the following properties are true. 1. The additive identity is unique. That is, if v plus u is equal to v, then u is equal to 0. 2. The additive inverse of v is unique. That is, if v plus u is equal to 0, then u is equal to negative v. 3. 0 times v is equal to 0. Number 4. C multiplied by 0 is equal to 0. 5. If CV is equal to 0, then C is equal to 0 or V is equal to 0. 6. Negative times negative of V is equal to V. Let's prove the first property. Assume that V plus U is equal to V. V plus U is equal to V is the given. Then add the negative V to both sides. It became V plus U plus negative V is equal to V plus negative V. Then v plus u plus negative v is equal to 0 under an additive inverse. So v plus u plus negative v is equal to 0 under associative property. V plus negative v plus u is equal to 0 under commutative property. Then v plus negative v plus u is equal to 0 under associative property. Then 0 plus u is equal to 0, commutative property. U is equal to 0, additive identity. That's all for today. Thank you for listening.